Hi everyone and welcome back to my channel A in Economics. So today we will study about the Durbin Watson test, which is also known as the DW test for detecting autocorrelation. And this is going to be our lecture number 17 on econometrics. If you haven't watched my previous videos, I would recommend you to do so. I'll give the link in the description and I'll also add the playlist on the I tab button so you can check that out, right? This is going to be our final video on autocorrelation, and from the next day onwards, we'll be starting off with multicollinearity, right? So let's quickly see what is the Durbin Watson test, which is most famously known as the DW test. And this is the most famous test for detecting autocorrelation or the serial correlation in case of time series data or any sort of data set, right? So let's see. The most important test for detecting serial autocorrelation is that developed by Durbin and Watson. So they were two different econometricians. They developed this test in their paper. Now this is a bound test. Now why this is a bound test? When we will derive the statistic, the test statistic, you will see that test statistic will lie within a specific bound, within a specific range, and that is why it is called the bound test, which is used to detect autocorrelation for the first order autoregressive process. So this is one of the most important consideration, that DW test can be applied only for the first order autoregressive processes that I'll introduce in a while. First order autoregressive means the maximum lag value has to be 1, right? Maximum lag value has to be 1, and only in those sort of regression models we can use the DW test, right? So let's formally start with the model and see how to apply this test to see autocorrelation is present or not in our model. So the model we will use looks something like this. Yt equals to beta 1 plus beta 2 x 2t plus beta 3 x 3t plus beta k x kt plus some ut plus some error term, right? Where ut will take a particular form. Ut will be rho ut minus 1 plus some et. Also, the mod value of rho has to be less than 1, which basically means that rho lies between minus 1 to plus 1, right? So this is the general structure of our model. If you remember what I have told you, first order autoregressive process means the lag value is of order 1. See here ut is the error term, stochastic error term, which is dependent on its lag value of the first order. Ut is a function of ut minus 1. So it is the lag value, its own lag value of the first order, right? So maximum order that can be taken by ut, that is only 1 in this particular case. And this is the general structure of our model. And if you again remember that this is the AR1 process, autoregressive process of order 1. If you have seen my time series videos, you will remember I have proved there that when the rho, that is this coefficient, when this coefficient lies between minus 1 to plus 1, this autoregressive process is weakly stationary, right? This autoregressive process is weakly stationary when the mod value of this rho is less than 1, which is rho lies between minus 1 to plus 1. So we will consider a weakly stationary autoregressive process and then we will proceed, right? So this is the general structure of our model. So where what we understood is that this is the model where ut is the stochastic error term and ut is dependent with its own lag value of the first order in this particular linear fashion. In this linear fashion, and et is another error term. Et is another error term. Et does not have any kind of autocorrelation, but ut suffers from autocorrelation. So we want to check that this autocorrelation is significant or not. It can significantly affect our model or not, right? So that is what we want to test. Now for that we have to define the hypothesis and the test statistic. So what will be the hypothesis? The null hypothesis would be, in the null hypothesis, as we always do, we will say that there is no autocorrelation present in our model. So we will say rho value is exactly equals to 0. Now please understand this thing. If this rho value is 0, which means that ut is just similar to et, so there is no autocorrelation present in our model. So null hypothesis always assumes that there is no autocorrelation present in our model and this rho value is exactly equals to 0. Against the alternative, what would be the alternative hypothesis? Let's see. The alternative hypothesis can be of two ways. First could be, suppose one is H1, where rho is positive, which basically means that positive autocorrelation is present in our model. Or you can say that H2 is another alternative hypothesis where this rho is strictly less than 0, which means negative autocorrelation is present in our model, right? So alternative hypothesis can be in either of the two ways, right? Null hypothesis, in null hypothesis, we always assume that there is no autocorrelation. There is no autocorrelation present in our model. But in alternative, we can either check for positive autocorrelation or we could check for negative autocorrelation. And depending on the alternative hypothesis we choose, we will see how the decision rule changes, right? So this is the general structure of the model. And now the most important thing is the test statistic. What would be the test statistic? The test statistic under the null hypothesis H naught equals to 0 would be T statistic, D, the small letter d, which is defined as summation T from 2 to n. It will not start from 1, it will start from 2. Ut cap minus ut minus 1 cap whole square upon summation T from 1 to n ut cap whole square. Right? So this is the general structure of the T statistic, which is under H naught, which follow D statistic or DW statistic, basically. DW distribution, basically, right? So this is the distribution that is defined by Durbin and Watson. That is why it is the DW statistic. So we'll assume that rho value is equals to 0 while defining the test statistic. So any kind of test statistic is always defined assuming that the null hypothesis holds. And this is also the same. So this is the general structure of the D statistic. This is the D statistic where see here we start the T to be from 2 to n. Why this is 2? Because here see here you have a lag value, right? Here if you put T equals to 1, this will be U0, right? The suffix will be 0. That doesn't make any sense. T can start from 1. So to make it 1, it should be starting from 2. Right? So U2 cap minus U1 cap whole square will be the first term, right? So this is the general structure of the D statistic, where what we can say is that this UT cap is nothing but UT cap is the OLS residual, right? This UT caps, whatever be the suffix, it could be T, it could be T minus 1. These are the two suffix. This UTs are the OLS residual, right? Okay. So this was about our hypothesis and the test statistic. Now let us come to the test procedure, how to proceed and see the decision rule. So first case that we will consider, as I have told you, since we are dealing with the two different alternative hypotheses. Here we have two different alternative hypotheses. So first let us see what will be the decision rule under this particular hypothesis, alternative hypothesis, and then in the second case we'll see what will be in this particular case, right? So there will be two different cases. The first case is when the alternative hypothesis is rho greater than 0, right? So under this case, the decision rule is as follows. What will be the decision rules? The first case would be to reject H naught if the D value is less than DL, where this DL is the lower bound, of the DW statistic or the test. This is the first case. We have to reject H naught if the statistic value, I mean D means the computed statistic value is less than the predefined lower bound. This predefined lower bound and the predefined upper bound can be found out using the distribution table that is given by Durbin and Watson, right? So this is the case. And if we reject H naught, we will say, and we will conclude that there is significant, positive autocorrelation present, right? So this is the first case where we will say that if the D statistic value, computed value, is less than some predefined lower bound of the DW statistic, then what will happen? We will conclude that yes, there does exist significant positive autocorrelation in our model, since we are checking for positive autocorrelation, right? Now there is a second possibility. If the D value is greater than the upper bound, if this D is greater than the upper bound, I'm not writing this again, this will be the upper bound here, then we can't reject H naught, then we cannot reject H naught and conclude no autocorrelation, and we will conclude that there is no autocorrelation present, right? So this is the second case. When the computed value is greater than the upper bound, some specific predefined upper bound, we'll say we cannot reject H naught and there is no autocorrelation, significant autocorrelation present in our model. And there is a third case where the test becomes inconclusive, right? If the D statistic value, computed value, lies between the lower bound and the upper bound. If this is the case, what we will happen? We will say that the test result is inconclusive. The test result is inconclusive. We cannot say anything. The test fails. The test fails. Right? So these are the three cases under the alternative hypothesis rho is greater than 0. I hope these three things are absolutely clear, where this lower bound and the upper bound will be given in the table that is provided by Durbin and Watson, right? And these values will vary with the number of observations that we use, also the number of explanatory variables that are there in the regression model, right? So let me write it that du and dl, they are predefined. They are predefined, can be found from the table, depends on firstly the number of variables, that is the number of observations. N is the total number of observations that are there in the model. They depend on N, also number of explanatory variables in our model, right? Explanatory variables in our model. So these are the two things that will determine the upper bound and the lower bound of the D statistic value, which has to be predefined before going into the test, right? Before going into the test, you have to define what is the lower bound and what is the upper bound of the statistic that we are going to use, depending upon the number of observations that we are undertaking and also the number of explanatory variables, right? So now let's go into the second case, that is case B, where our alternative hypothesis is H2 rho is less than 0. That is, we are checking for the negative autocorrelation. Here, what will be the decision rules? See, decision rules are given by firstly, reject H naught. We will reject H naught if the computed D value is greater than 4 minus DL. 4 minus DL, and conclude that there is significant negative autocorrelation is present, right? So this is the first case when D computed value is strictly greater than 4 minus DL. DL is the lower bound. again, then we will conclude that there is significant negative autocorrelation. Since we are testing for negative autocorrelation here, we'll say that yes, significant negative autocorrelation is present in our model. Now, the second case would be when the d value is strictly less than 4 minus du. If d statistic value is strictly less than 4 minus du, we cannot reject H naught. We cannot reject H naught, and we conclude no autocorrelation. That is, null hypothesis is true basically, no autocorrelation present, right? And there is a third case when the test becomes inconclusive if the value lies between this. If this is the range, if the d statistic value, computed value lies between 4 minus du to 4 minus dl, if it lies between this range, then we cannot say anything and the test fails. The test fails and it is inconclusive, right? This is inconclusive. We cannot say whether autocorrelation present or not. So what we got is that there are two inconclusive regions. This is the first inconclusive region and this is the second inconclusive region, which is one of the most important drawbacks of this test, that if the computed d statistic value falls between these two ranges, then we cannot apply this method and the test fails. Right now we can, depict all this test procedure in a diagram. Let's see this diagram here. Suppose we measure the d statistic value here on this x-axis, and here we have f of d. Right now we can, define the specific values of d that we got earlier. So suppose this is dl. This is the lower bound that we consider. Suppose this is the upper bound. Suppose this is 4 minus du. Suppose this is 4 minus dl. And suppose this value is 4. So later on we will prove that this d statistic value always lies between 0 and 4. See here, the minimum value that I have written is 0 and the maximum value that I have written is 4. So why this is so, we will come to that. I will derive that in a while. Now please understand how to make this diagram. So what we can say is that here this du and dl, I have taken this according to there is no scale for that. For different problems you will have different values of dl and du, as I have told you, depending on the number of observations that you are taking in your experiments and the number of explanatory degrees. So here the values are imaginary. Here I have randomly taken some values, marked some values here. So what we can see from the diagram is that if the computed value of d statistic lies within this range, 0 to dl, then we will say there is positive autocorrelation, right? If this is between 0 and dl, we will say this is positive autocorrelation. If this is between this to this computed value, then there is no autocorrelation. And if the value lies between this to this, there is negative autocorrelation. Not only that, there are two regions. This is one region where the test fails, that is inconclusive. Inconclusive region. And there is another region, this and this. This is also an inconclusive region, right? These are the two inconclusive regions. And this is how you depict the DW test using a diagram. So this diagram, this figure is depicting Durbin Watson test. This is the formal diagram that we use to clearly define the decision rule. This diagram basically shows the decision rule that you have to use. So if your d statistic value, you can take it to be the rule of thumb as of now. I'll derive how this comes. Why the value lies between 0 and 4, that is why it is called a bound test. I'll come to that in a while. But as of now, please understand, if the computed value of these statistic lies between 0 to DL, that is the lower bound, then we'll say that yes, positive autocorrelation is present. The better the value, more close it is towards 0, the more positive autocorrelation present in our model. If it lies between du to 4 minus du, there will be no autocorrelation. And from 4 minus dl to 4, there is negative autocorrelation present in our model, and there are two inconclusive regions. This is the first region and this is the second region where we cannot say n. Right? I hope this much is absolutely fine. If you have any questions anywhere, you can let me know. Now the final thing is the rationale. Now I'll show you how to get the bound for the DW test statistic. So for that, we will start with the statistic itself. So what was the statistic? Statistic was t from 2 to n ut cap minus ut minus 1 cap whole square upon summation ut cap square, right? This was the statistic. Now you can expand the whole square. So this will be ut cap square plus t from 2 to n ut minus 1 cap square minus 2 summation t from 2 to n ut cap ut minus 1 cap, and the denominator remains the same, ut cap square, right? This is so. Now, what we will say is that for n tends to infinity, when this n tends to infinity, can you say what will this value be? You can pause the video, you can think for yourself. When n tends to infinity, there is this upper bound, this tends to infinity, what will happen to these expressions? So when n tends to infinity, summation t from 2 to n ut cap squared will be approximately equal to t from 2 to n ut minus 1 cap square. Why this is so? Let me give you a simple example. This is a property of infinite series. So when n tends to infinity, all this series becomes infinite series because the upper bound is infinity. So every series that you see here, this series, this series, this series, every series goes towards infinity. Now for infinite series, we have a property that suppose 1 plus 2 plus 3, if you add this thing up to infinity, and now suppose I drop this first term and I start from 2, 2 plus 3 plus, and again it goes to infinity. Now you drop the first term and compute from 3 plus 4 up to infinity. Then according to the property of infinite series, all these series will have the same value approximately, because you are summing them up to infinity, right? So the difference of each of the series will be very minor because you are only dropping one of the terms, which is a very small value. 1 is very small compared to infinity, 2 is very small compared to infinity, 3 is also very small compared to infinity. So if you sum all these values, the approximate sum of all this series, all this infinite series will approximately will be equal. I'm not saying they will be exactly equal. They will approximately will be equal because you are dropping out a very small term from them. So the entire sum will not be very different, right? So this is the exactly same thing we are doing here. Whether you start from the suffix t or you start from the suffix t minus 1, it doesn't matter. If you drop one of the terms, the sum will exactly will not match, but they will approximately be equal. So this is the approximate sign. This and this two wavy lines, they are the approximate signs, right? I hope this much is understood. So this term and this term, they are almost equal. That is what I am trying to say. So if this is the case, now you can reduce the D statistic in this way. You can simplify this thing. So this will be approximately equals to, not exactly equals to. This will be approximately equals to summation ut cap square upon summation ut cap square plus the second term will also be ut cap square. Ut cap square upon ut cap square. So I'm, basically applying this denominator to each of these terms, this, and this, right? So what I'm saying is that this term and this term are approximately equal. So you can replace that with summation ut minus 1 cap square can be replaced by summation ut cap square. And the last term, will remain as it is. Ut cap ut minus 1 cap upon summation ut cap square, right? This is what we have. Now, if you simplify, you will see this terms and this terms will vanish. So this will be 1 and this will be 1. So 1 plus 1, you have 2 and then you have the rest of the terms. Let me write it here. So the value of the statistic will be 2 minus 2 and then you have ut cap ut minus 1 cap upon summation ut cap square. So D will be approximately, take this 2 out. So 1 minus summation ut cap ut minus 1 cap upon summation ut cap square. I hope this much is absolutely fine. Now what we can do, we can do some rough calculations. What we know is that covariance of ut cap ut minus 1 cap is 1 by n summation ut cap ut minus 1 cap minus ut cap bar ut cap bar into ut minus 1 cap bar, right? So this is basically summation 1 by n summation ut cap ut minus 1 cap minus this. This is the, formula. Actually, what you can do, this is the formula, summation ut cap minus ut cap bar into ut minus 1 cap minus ut minus 1 cap bar. So basically, this is the formula, and if you simplify this, you will get this particular. This is the reduced term for the covariance, right? Now, what you know that this terms will be 0. This terms, so the basically the average of the residuals, the average of the residuals are always 0. So this term will vanish, and you will be left with only this 1 by n summation ut cap ut minus 1 cap. That will be covariance of ut cap and ut minus 1, so minus 1 cap. We'll understand in a while why I am doing this. This is our first relationship. Now we need a second relationship, that is variance of ut cap. This is the second thing that we need. That is 1 by n summation t ut cap square minus ut cap bar whole square. That is also the variance formula. Basically, I am expanding this thing. Ut cap minus ut cap bar whole square. So if you expand this, you will get this reduced term here. So again, this ut cap bar, this term is 0, so we'll be left with only the first term. So variance of ut cap will be simply 1 by n summation t ut cap square. And this is the second relationship. Now, what is rho ut cap ut minus 1 cap? This is simply covariance of ut cap ut minus 1 cap upon root over of variance of ut cap root over variance of ut minus 1 cap. This is the correlation coefficient. This is the correlation coefficient of the first order, basically. See, the correlation coefficient or the autocorrelation, you can consider this to be the autocorrelation between ut cap and ut minus 1. Now, what you have from the relationship is that covariance of ut cap ut minus 1 is simply this. So let me write it. Let me write it here. 1 by n summation ut cap ut minus 1 cap, and the variance, from the variance formula you have this. So if you multiply it 2 times, then it will be simply this. So variance of ut cap and variance of ut minus 1 cap will be almost same, only the suffix will change. So again, if we consider n to be infinity, they will be almost the same. And then square root, if you multiply the square root, then it will be only this particular term. I hope you can do this calculation. So this thing will cancel out and you will be left with only this ut cap ut minus 1 cap summation ut cap square. And this is simply the correlation between ut and ut minus 1. Now, this is a very crucial relationship. From this, can you remember something where we got this expression? See, this is the same expression we got here while calculating the D statistic, right? This is the same relationship. So instead of this, we can replace, so instead of this entire thing, we can replace rho, right? We can replace the rho or rho cap, whatever you call it. So from that relationship, we had D will be approximately equals to 2 into 1 minus summation ut cap, ut minus 1 cap, summation ut cap square, and that will be 2, 1 minus simply rho cap, right? Rho cap is nothing but this particular thing. This is the estimated value. Rho is the value, rho is the statistic, and rho cap is the estimated value of that. Since we are estimating this rho cap, see, they depend on the residuals, and residual means estimated error. So everything that you do here is estimated. That is why this cap is valid. Cap means you are estimating something. So here this rho is estimated, and hence it is rho cap, right? So rho cap, as I have told you, is the first order autocorrelation between ut cap and ut minus 1 cap, right? I mean the residuals, right? Now consider this thing. This rho cap is the correlation coefficient, or the correlation basically. This is the correlation. And as we know from the properties of correlation, that correlation always lies between -1 to +1. And also, since it is rho, and in the very first slide, I have said that we have assumed that mod rho is less than 1, right? Let me get back to the slide once. See here, I have defined this to be, I have assumed, this is assumption, right? This is our assumption. Or if you don't assume also, we'll know that correlation coefficient always lies between -1 to +1. From that also you can see. So this rho lies between -1 to +1. If that is the case, then what will be the bound for D? So let's take the values. If the value of rho cap is exactly equals to 1, what will be the D value? 2 into 1 minus 1, that is exactly equals to 0. And if the rho cap value is -1, then what will be the value? 2 into 1 minus minus will be plus, so 2 into 2 is 4. So that is how you can derive that 0 less than D less than 4. Right? So the D statistic or the DW statistic, Durbin Watson test statistic, always lies between 0 to 4. I hope this thing is absolutely clear to you. This is the process. That is why it is called a bound test. On the very first slide, I have told that Durbin Watson test is a bound test. Why this is bound? Because you have a specific bound in which this D statistic value will vary. And also in the diagram, you have seen that this value lies between 0 to 4. And this is the rationale behind it, right? Now, how did we get into the decision rules? The decision rules are made in this particular fashion. Let me write the cases for you. If there is no autocorrelation, what we will have? We will have the rho value to be exactly equals to 0, as we have defined in our null hypothesis. This is the estimate. This is not a null hypothesis. This is the estimated value of the rho. So if there is no autocorrelation, then this rho value has to be 0, which basically means if for the sample data, we have D star, that is the computed value of D to be exactly equals to 2, then we accept that there is no autocorrelation, right? Now case 2, If the rho cap value is exactly equals to 1, as I have told you, D star value will be exactly 0, and we will have a perfectly positive autocorrelation. I'm not writing it again, perfectly positive autocorrelation, perfectly positive. There will be perfectly positive autocorrelation. So if, as long as 0 less than D star less than 2, some degree of positive autocorrelation is always present, right? Some degree of positive autocorrelation is always present, and it becomes stronger and stronger as the value of D star approaches to 0, right? This we have seen in the diagram also. See here, as long as the value of the D statistic lies between 0 to 2, 0 to 2, then there will be some degree of positive autocorrelation present, and it will be stronger and stronger as the value approaches 0, right? As the D statistic value, that is the computed value. This value means the computed value of the D statistic approaches 0, approaches towards 0, the strength of the positive autocorrelation will be stronger. It will be more strong, right? So this is the second case, and there is a third case. If the rho cap value is exactly -1, D star value is exactly 4, which is perfectly negative autocorrelation, perfectly negative autocorrelation. And as long as this value lies between 0 to 4, some degree of negative autocorrelation is present, and it gets stronger and stronger as the D star value approaches towards 4. Again, let me show you in the diagram. So please remember this using this diagram. I find this diagrammatic approach more useful because, remembering all this decision rule is, I know it's a little hard, but once you, internalize this diagram, it becomes very easy. So please take a screenshot or, manually write it, and you will understand the thing, right? So as the D value keep on approaching towards 4, the negative autocorrelation becomes stronger and stronger. So these are the two things. If the D statistic value lies between 0 to 2, there will be some degree of positive autocorrelation. If it is exactly 2, see here, I have written this, that if it is exactly 2, then there is no autocorrelation. If it lies between 0 to 2, there is some degree of positive autocorrelation. If it is between 2 to 4, there is some degree of negative autocorrelation that is present in our model, right? So this is the rationale of the test, and for your simplicity, you can remember this particular expression. This particular expression will help you to get along, right? If you remember this, you can substitute the values of rho here. Rho cap, basically, if you substitute the values of rho cap, you will get the appropriate D statistic range. And these are the range that basically will be required for you, right? These are the things that will be required to get into conclusion. So this is about the method, this is about the approach that we use. Now, this approach, though it is widely used, it is not free from limitations. There are some severe limitations that we have in this model. What are the limitations? I have listed all the 4 limitations. The first limitation would be not applicable. This test is not applicable when the explanatory variables are stochastic in repeated sampling. So the X value, explanatory means the X values. If they are stochastic, then it will not be a valid approach. This can only be used when the explanatory variables are non-stochastic, which means they do not have any probability distribution. Stochastic means they have some probability distribution, but for this test to be applicable, the explanatory variables has to be non-stochastic, which means there are some fixed values in repeated sampling and they do not have any probability distribution. Only in that case you can apply this method. Now the second thing is that in case of lagged dependent regression models, we cannot apply this test. What is lag dependency? Suppose, for example, consider the model YT alpha plus beta, say YT minus 1 plus epsilon t, or say UT. Right? If you have this kind of a model, this is a lag dependent model. Lag dependent regression model means that you have the YT is dependent on its own lag value, right? own lag value of order 1, it can be of higher order also. It could be alpha plus beta yt minus 1 plus gamma yt minus 2 and so on, right? It could be of higher order also, but this is the general structure of a lag dependent model. So if your dependent variable is dependent on some lagged value of its own, of some order, then this method, this DW test is not valid. What will be the consequence of that? If this kind of a model is taken under consideration, it can be shown that the combination of the lag dependent variables. So basically yt minus 1, if you consider higher order lag, so yt minus 2, yt minus 3. So these lag dependent variables and the positively correlated disturbance terms, that is UTs, they will be they will create a bias. They will create a bias, and this DW statistic will be upward biased. The value will be inflated, right? There will be an upward bias. The value of the DW statistic will be inflated, and this will give you misleading conclusions, right? That is the consequence. That is why you cannot use lag dependent regression models. There is a specific proof of this particular consequence. If you want, I can do this in some separate video. But for your undergraduate and postgraduate level, I don't think you need the proof. That is why I haven't included this in my lecture. If you want, you can write me in the comment section. I can provide the proof also. So what happens is that if you use the lag dependent regression model, then these lag terms of first order or the higher orders will be they will interact with the positively correlated disturbance term, that is UT cap, and they will bias the DW statistic upward. There will be an upward bias that will be created, and that will give you misleading conclusion. So that is why we cannot use lag dependent models. Third, and the most severe consequences limitation is inconclusive region. There are some specific regions where we cannot comment anything using this DW statistic. As I have told you, there are two regions. First is this. When the D statistic value lies between the lower bound and upper bound. This is one of the inconclusive regions. And the other one is this, 4 minus DL, right? These are the two inconclusive regions. If the computed value of D statistic falls in these two regions, you cannot comment anything on the consequence or you cannot detect autocorrelation. So this is one of the limitations. If this thing is present, inconclusive region is present in your model, what you can do, you can use some alternative test. For example, Bruce Godfrey test is basically used for higher order autocorrelations, or you can use the L-Jung box test also, right? These are the two alternative tests that you can use for higher order autocorrelations: L-Jung box test or Bruce Godfrey test, right? And the last and the final thing is that in DW test, we assume that the disturbance terms are generated by the first order autoregressive process. So when I defined the model, let me get back to the model. I have specified that this process, the model that we use, should be of the AR1 type of model, right? Autoregressive process of order 1, the maximum lag value that you can include in this model is 1. So this test is applicable only for the first order autoregressive process. So we'll assume that the disturbance terms are generated by this first order autoregressive process only. So this test cannot be used to detect higher order autoregressive processes. And as I have told you, if higher order autoregressive processes are used, you have to use some alternative approaches. For example, as I have told you, L-Jung box test and Bruce-Godfrey test, right? So that is all from my side for today. I hope you enjoyed this lecture. You got some insights, useful insights. If you have any questions anywhere, you can let me know. And by this, I have finished the autocorrelation chapter. From the next lecture, I'll be starting with multicollinearity. And if you like this video, please give me a like and do subscribe to this channel, AN Economist. And this gives me immense motivation to continue making videos for you. And this will also help me to grow my channel, right? So if you want me to keep on making these useful videos, please support my channel, subscribe, subscribe to this channel. This is absolutely free of cost. And I hope to see you in the next lecture. Thank you for your time.